So let's get on with the rest of the next two. So here's, actually, where's this? This is just showing a rechargeable battery station. So taking the electromagnetic energy that we just talked about and turning it essentially into chemical energy inside a battery. Okay, so next. And if you stick with electronics, we can get into series and parallel systems. Inside a solar cell, all those cells that you see behind you, each one of them is going to get to about a half a volt. If you want to get up to, let's see, 0.5, 1, 2, 3, if you want to get up to 4 volts, there it is, you need to put the 0.5 voltage deals in series. And remember, I talked about voltage as sort of pushing. You can think of each one of these as like a person or a horse or whatever, sort of playing tug of war. You add them up in a line, you get more force. You add them up in parallel, and just sort of think of a stream. If you ever walk along the Rattlesnake Creek, you'll see, okay, there's the main channel, then there's this other one. Well, you add all that up, and you get more current. So there's an example of series and parallel. So the photons flow in here, pop the electrons up into those metallic shells we talked about, and charge your device. Okay, so that kind of takes us to chemistry. As Matt was saying, they used to have competitions so you could name all the chemical elements, and it's a good challenge. Just draw this out blank someday, and if you're bored, write them in along with the numbers. There's a lot going on there. What always fascinates me, we've only known this for 160, 170 years. Mendeleev put this thing together in the 1850s. It's amazing. There it is. Okay, so chemical energy typically we think of as something burning. Coal is chemical energy. We'll look at that soon. Oil is chemical energy. Natural gas, we talked about a little bit before lecture. There's your methane molecule. And what happens with chemical energy? And let's just look at methane combustion really quick. So here's your methane molecule. You got a single carbon there. You've got hydrogen stuck to it. You can go back and verify that, but there are 4 openings for carbon on the dynamic periodic table. Go back and take another peek at that. I don't know why this thing got so small all of a sudden. Let's just look at carbon. Sorry this is so small here, but you can see in these 2 little boxes, there's an up electron, so missing down, and a missing pair. And so there are 4 places for that hydrogen electron, that single lonely little electron, to bind. And there it is. There's your methane. Well, what happens when you burn methane? Atmosphere is 80% nitrogen, 20% oxygen. It's combining with the oxygen. There's oxygen, O2. I drew that double bond because that's roughly what it looks like. Oxygen is missing a pair of electrons in its 2p orbital, but if you bring another oxygen atom close to it, not that you could, I mean they bump into each other just quite readily without us moving them anywhere. The 2 are essentially shared. The 2 extra become the 2 that fulfill those or fill up those other 2 orbitals. So from there, what happens when they burn? Well, what are the products of combustion? We know CO2 is one of them. So there's your CO2. Here's carbon. It has 4 bonds. There's oxygen and water. H2O, pretty innocuous, right? Plants need that to breathe, and everybody loves water. Well, some cats don't. There's your H2O. The only thing left to do is notice that, well, we have a carbon atom on the right, we've got a carbon atom on the left. That seems fine, no problem there. we've got 3 oxygen atoms on the right and only 2 on the left. That's a problem. And we also have a deficiency in the number of hydrogen atoms. We've got 2 on the right, but 4 on the left. So let's just draw in another water molecule. Okay, so now we've got 4 hydrogens on both sides, looking good. 1 carbon on both sides. And now that we've put in that second water molecule, we actually have 4 oxygens on the right, but whoopsies, only 2 oxygens on the left. So let's just add another oxygen molecule. And now we're in good shape. So this tells us if I'm going to completely burn a methane molecule, I'm going to have to give it 2 oxygen molecules. So that's chemical energy. And what comes off? Heat. And what would you use heat for? Well, you could use heat to make steam. What would you use steam for? Well, you could spin a turbine. Why would you want to spin a turbine? Well, so you can go back and get those magnets spinning. Why do you want magnets to spin? Well, so you can make electricity. What's that good for? Well, keeping the lights on, running your laptop, et cetera, et cetera. Or stay warm. So, fundamentally, the majority of our energy we use is chemical. Coal, oil, natural gas, and it doesn't really get much simpler than burning methane. Coal, there's all kinds of stuff in there, oil, all kinds of stuff, much larger molecules, but it's still, fundamentally, this is all it's coming down to. You're just, putting it in your oxygen, letting it catch fire, and something moves. Okay. There's chemical. Yeah, sort of a tidier picture than what I just drew, but that's what they're showing. They drew the carbon is black, the hydrogen's white, the oxygen's green, and there's your pair of oxygen molecules to get your combustion. All right. Here's Rutherford, a little bit. Ernest Rutherford, born and educated in New Zealand, joined the Cavendish Laboratory in 1895, and after periods in Montreal and Manchester, returned as director. A large, exuberant man, he attracted lively groups of students and co-workers. The radical change from a picture of matter consisting of different uncuttable atoms to one in which all atoms are built from just a few fundamental particles was largely his, and regarded him as the founding father of physics. So in a lot of ways, what Rutherford did, he sort of saw the beauty of what Mendeleev put together, and each one of these numbers just said, oh, there's just 28 protons sitting down there, and it's pretty simple. 3 fundamental particles: proton, neutron, electron. That's your recipe for making the entire periodic table. There have been people that dig down farther and talk about quarks and et cetera, but that was really, things were very confusing to a large extent. Rutherford simplified it and just said, hey, there's photons, neutrons, and some of the experiments he did, he actually detected individual nuclei. So sometimes the particle flies through and sometimes it doesn't. It's like, what did it just hit? Well, it hit the nucleus. What the heck's a nucleus? Well, there it is. Okay. So there's Rutherford. All right. So the only thing left to cover now, and I'm obviously not going to give it do it complete justice here, but we will have a full 2 chapters on nuclear energy. So we've covered mechanical, we've covered thermal, we've covered electrical, we've covered chemical, we've covered electromagnetic. The next one is just atomic energy. So there is the nucleus itself. Protons define the charge of the nucleus, which then sort of dictates how many electrons are flying around the orbital. And then the neutrons are there in some ways to shield the protons from just flying apart, because they've got this positive charge. They do not want to be together. The neutrons sort of allow them to be together. They're not so dang close that they just fly apart. That's more or less the purpose of the neutron as I understand it. Here's Einstein. And so what Einstein actually came up with, this is certainly no secret, but it's just that E equals mc squared. And so the thing that I really want to draw your attention to, and we'll dig into this in more detail, and this is in a lot of ways kind of the bread and butter of the energy technologist, if you will. So energy density. It's one of my favorite figures. And if we just kind of scroll down here, click on that guy, hopefully we get a bigger picture of it. This figure that we're looking at online is a more complete picture of the table in your textbook that's given in table 4.3. So if we look at table 4.3, 4.3, pardon my handwriting, table 4.3, it's energy density. So let's just go out, and it's saying, how much energy to store 15 terajoules. So this is equal to 15 times 10 to the 12th joules. And I'm trying to remember why they chose that 15 terajoules. If we go back, if you go back, that's the problem that was worked in 4.3. So the question is, like, how much of these chemicals do you need to do this 15 terajoules of water that was stored, in the Gordon Butte project, or one of these pumped hydro projects. So, let's just say for hydrogen, we're looking at 110 tons. Now, let's just go back to the website and say, okay, I can see that because hydrogen is way over here with a very high megajoules per kilogram. Hydrogen has a relatively high energy density. If we go back, what's the next one that's given? Methane. So this is H2. Methane is 270 tons. That's CH4. We just did the combustion of methane. So, 2.5, roughly 3 times. Does that make sense based on what we're looking at here? Well, here's natural gas right there. And here it is at 50. Multiply 50 by 3, and yeah, you're right up there around 150 or so. So fortunately the book and the Wikipedia match each other. What's the next one? Oil. You're going to need 360. Let's write that one down. 360 tons. So the numbers get bigger, which means that the energy density gets smaller. There's less energy per unit oil than these other ones. And let's just see, does that match the online figures? There's natural gas somewhere in here. Let me know if you see it. Here's gasoline and diesel.
Natural gas is way low.
It's way low?
Well, it's below that.
Oh, well, yeah, so here's the point. To the right is high and to the left is low. Because right now, the units that we're dealing with are in tons. This axis, and thanks for bringing that up, this axis is per liter, if you had a liter of it. Yeah, so there's 2 different ways of looking at energy density. And so if you think back to summary 1, the units I used, it was energy per cubic meter, per 1,000 liters. So you can look at it in either way, and that's exactly what they're allowing us to do with this figure. We can look at it in either way, on a per mass basis or a per volume basis. How much it weighs versus how much space it takes up. Think feathers and cannonballs. Yeah. Okay. And I don't see oil on here, but as we know, as the Canadian Atomic Energy Commission pointed out, Brad Layton doesn't know what he's talking about because he said that oil is 4 times more dense than gasoline and diesel, but we know they're on the same order of magnitude. So, down here, a few percentage, and that's, that's what we're seeing there. Maybe.
Do you still stand by your numbers?
Well, I have publicly stated that I failed to mention in my paper the loss of efficiency. Yeah, I mean, I don't have to stand by my numbers because they're correct. I mean, everybody knows exactly how efficient internal combustion engine is moving through space and time. So I just, noted that I didn't explain it well. But the point I want to make here, and then I'll let you go, is that uranium, so U-235, we're talking 25 kilograms. So there's your, so this is, a small fraction of a ton. So so what we're looking at is 25 divided by 1,000 equals 0.025 tons. So we're looking at 6 orders of magnitude less uranium to, and this is exactly what happens in a nuclear power plant. That uranium degrades into other elements. It's gone. Did you burn it? Well, not really. You didn't put oxygen in there and burn it, but did you degrade it? Yeah. It's gone in the same way that when we burn methane and oil and coal, we destroyed it. We destroyed those chemical bonds. In the case of uranium or nuclear, we're destroying those nuclei that were shoved together in a supernova 10 billion years ago. Kind of wild. Okay, that's it for today. Thanks. Exam 2 will be open. Have at it, and I'll see you Tuesday.